Hey everyone, welcome to this explainer. I'm really thrilled you're here. Today, we're diving straight into a pretty fascinating investigative synthesis. We are looking at the structural geometry of salvaging legacy data, and we're talking about both macrosystemic logs and micropersonal chat histories, and how we can use them to build highly specialized diagnostic neural networks. I'll be your guide as we navigate this complex terrain, and we're going to keep our inquiry focused and razor-sharp. So let's just jump right into it.
Here's our investigative roadmap for today. We'll be looking at salvaging legacy data through a few differing AI cognitive geometries, moving from the concept of a digital fossil record all the way through to our explicit uncertainty zones. Okay, let's get moving.
Starting us off, let's look at the digital fossil record.
Now, usually, we tend to think of archaic system logs or old chat histories as just digital exhaust, right? Like useless byproducts of an active system. But the empirical historian AI completely flips that idea on its head. It actually frames this legacy microdata as a perfect fossil record of organic behavior, failure modes, and feedback loops before modern optimization algorithms altered them. Just think about that for a second. These logs aren't trash. They actually contain the vital structural DNA of your system, captured right before layers of modern sanitization kind of painted over the cracks.
And this brilliantly illustrates exactly why we have to look backwards. Think about sanitized modern data. It's highly optimized, it's incredibly clean, but it's often entirely stripped of the very friction that tells us how a system actually operates organically. Contrast that with raw legacy data. It's messy, sure, but it is totally unfiltered. To really uncover raw systemic behaviors, we absolutely need to extract the structural geometry buried inside that friction-filled raw data.
To pull that off, we're going to ride our inquiry over to the empirical historian's view.
So this is where we start using AI not as some simulated human persona, but strictly as a cognitive instrument. Let's define exactly what we mean by that. Cognitive geometry is basically the specific structural and analytical reasoning pattern of an AI model. We're mapping reality through structured cognitive diversity. And listen, we are completely avoiding platform tribalism here. We're not sitting around asking, hey, which AI is the smartest? Instead, we're asking, what specific structural patterns can this AI's unique geometry detect that all the others miss?
When the empirical historian actually aims its specific cognitive geometry at legacy chat data, it starts detecting anomalies that look exactly like systemic history. It mathematically maps the shape of lost redundancy, where a system used to have these safety buffers that have since degraded over time. It maps semantic rumination, which literally looks like looping, repeated questions buried in old logs. It can identify organic failure modes long before a total system crash even happens. It's literally out there finding the behavioral fossils.
But, of course, we need to introduce some friction into our investigation. Let's shift gears to the constraint modeler's reality.
Utilizing the specific convergent analytical geometry of Google Gemini, the constraint modeler kind of deconstructs the problem and hands us the harsh, brutal reality of salvaging all this data. Legacy macro and micro data is fundamentally unstructured and, frankly, incredibly noisy. It suffers from format rot. Are these old CSVs, outdated binary formats, just raw text? We honestly don't know. And training a modern neural network requires clean tensors, the pristine mathematical fuel for these models. To get those clean tensors out of this mess, you have to expend a massive amount of upfront computational energy just to harmonize the remnants.
So this leads us to a crucial fact-based conflict. On one hand, the mechanisms expert and the historian see immense high value here. They see us extracting structural DNA and behavioral fossils. But on the other hand, the constraint modeler sees immense high cost. They're looking at the massive computational load required for data harmonization versus the actual caloric efficiency of the resulting model. It's this brilliant tension, really, between the potential of the gold mine and the brutal cost of the mining itself.
To push that tension even further, let's stress test our assumptions with the adversarial critic's warning.
Using strictly skeptical reasoning, the critic immediately flags a massive risk. They call it speculative vacuity. This is the grave danger of assuming that just because legacy data is old and raw, it somehow inherently has structural value without actually taking the time to factor out obsolete biases. We run the risk of assuming we've found a crucial structural pattern, when in reality, we've just uncovered the ghost of a system that completely ceased to exist years ago. Let's really break down the critic's warnings here.
Often, legacy data simply captures archaic environmental friction. If you take a shiny new neural network and train it on the remnants of these obsolete systems, you are absolutely going to bake outdated biases directly into the new model's weights. You'll end up contaminating your brand new predictive tool with dead feedback loops. So before this data is even remotely useful, those external variables from the past have to be mathematically factored out.
So, how exactly do we synthesize this immense value with those brutal costs and severe risks? Well, we look to diagnostic micromodels.
And this right here is our breakthrough pivot. We should absolutely not use legacy data to train general AI models on how to operate today. Doing that just bakes in the obsolete biases. Instead, we use salvaged macro and micro data to train specialized neural networks purely on how systems decay. We aren't training them to run the ship, we're training them to listen to the hull for stress fractures. Here are the exact actionable steps formulated by the Meta AI mechanisms expert. Step 1. You feed a micromodel exclusively with those legacy failure logs. Step 2. You hypertune its cognitive geometry specifically to detect the absolute earliest mechanical shifts of a failing system. And finally, Step 3. You deploy it to identify real-time system degradation. We're talking about things like an increasingly erratic cadence in the logs or vocabulary narrowing in team chat histories. Those are real structural markers of a system under unsustainable stress.
We've reached a pretty powerful conclusion, but our framework always mandates intellectual humility, which brings us to our explicit uncertainty zones. Acknowledging what we don't know is totally a feature, not a bug of this structural analysis. So here are our zones of explicit uncertainty. First, missing perspectives. We still do not know the exact technical format of the salvaged data, which makes pre-processing calculations entirely theoretical at this point. Second, our fact-based conflict remains unresolved. We haven't mathematically proven that the diagnostic value outweighs the computational cost of cleaning the data. And finally, remaining uncertainty. We still need to prove that the archaic noise of dead systems won't just overpower the predictive value of these new micromodels. But hey, these aren't errors, these are our thrilled marching orders for the next stage of investigation.
By stripping away all those theatrical AI personas and instead utilizing specialized cognitive geometries, we've extracted the exact structural limits and mechanical utility of training new neural networks on legacy data. So I'm going to leave you with this to ponder. What hidden feedback loops, lost redundancies, and vital structural DNA might be buried right now in your own systemic exhaust? It just might be time to start looking at your digital fossils a little bit differently. Thanks so much for joining me on this explainer, and keep learning.